Okay guys, let's get started with branching and looping. So up until this point we've learned a little bit about our organization, we've learned about the instruction set, we've learned how to execute sequentially executed instructions, but we haven't learned how to make decisions. So that's what we're going to do in this chapter. Where we're going to start is probably with the easiest thing to start with, and that is the jump instruction. There are lots of jump instructions. This one happens to be the unconditional jump, which means it doesn't matter what has happened previously. If you get to this instruction, you will jump 100% of the time. So it corresponds, for those of you who have any familiarity with some older languages, maybe BASIC, Pascal, Fortran, oh my, really old languages, it corresponds to a go-to statement. Okay? And this statement label is the label. If I were to say top loop, whoops, and then have something, add EAX, EBX, something like that. So this is the instruction. I have several other things, and then I have jump, top loop. Statement label will be a label. So it's one of the parts of one of the pieces of an instruction we said is optional, and we said we would use it only when we needed to jump to a location in code. So here we finally get to use it. So that's what the unconditional jump is. I want us to look at the example code that's in the book. Figure 5.1, this piece of code has a problem. Let me show it to you real quick. Okay, this is what the code looks like, and the problem that it has is that if you notice, okay, so we initialize number to 0, sum to 0, we get here, execute, 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 jump back up to this, and we keep going around in a circle, and it never stops. So this is an infinite loop, okay? So it implements an infinite loop, which for a computer scientist is considered to be a very bad program design. When we're in class, we'll talk about why that may not be the case for embedded systems. So the other thing I want to point out to you about this is that this implements also a backward reference. What do I mean by that? Well, let me throw some numbers in here. If you'll notice, what if this first instruction occurs at this place in memory? We know that's an instruction that's going to take 6 bytes of for the opcode, mode RM, and for our immediate value. So 6 bytes to store it. When I add 6 to 25, I'm going to get 2B. So this is the address where the next instruction occurs. This one's also going to be 6 bytes. So when I add 6 bytes, I come up to this one. Okay? Here's the deal. When I get down to jump back up to forever, I am jumping from a location in memory. And at this point, once I've read this instruction, my instruction pointer has incremented by 2. So what's in EIP after I've looked at that instruction is actually 00A1 0035. So what I'm going to do is calculate an offset from where I'm at right now. I know I'm jumping. I'm going to take the destination minus the location of the jump plus 2 bytes. Okay, and that is how the machine is going to calculate the offset for your jump. By the way, this works for a backward reference because we're jumping from a higher place in memory to a lower place, or our offset is going to be negative, but it also works for a a forward reference. So works both ways, either way. In this case, well, let's see what else we've got, because I think I've got some opcodes to show you in just a second. So we'll do that. But before we get there, two major groups of jump statements: intersegment and intra-segment. Intersegment is the same as, for example, interstate highways. It goes between states. Intersegment jumps go between segments. In this course, we won't be doing much of those. We will be confining ourselves to intra, jumps within the same segment. Okay? So, for intrasegment jumps, these jumps contain the displacement of the target from the jump statement encoded in the instruction. So, and I want you to remember this. We have some other ways when we write jump statements to indicate where we're jumping to, but when we encode them, it's going to be important to remember this, okay? Because the machine is going to calculate the offset. From where I'm at right now, where am I going? I'm going to add that offset to what's in the EIP and then replace EIP with that, okay? So, I tell you what, let's go back. And let's see right here, okay? So we said it was destination, and we're jumping to this place in memory. So, 00, A1, 0030 minus the location of the instruction plus 2, 00A1, 0035. Okay, when I do this, 0 minus 5 I can't do. I'm going to borrow, loan that, so 16 minus 5 gives me what? Oh, it gives me a B. Okay, 2 minus 3 I can't do. I can't borrow from him, so I'm going to go over here, borrow the 1 from that guy, loan it to this guy. I'm going to borrow 1 from him, loan it to him, borrow 1 from him, loan it to that guy. So 1, 2 is 18 minus 3, which is 15. F, F, and you see where the rest of this is going. This is the same as minus 5. That is a small number, so my offset is going to be that size right there. It'll be FB. That'll be the second byte in the encoding of a jump instruction where I'm jumping to a location that's pretty close. So, since I've said pretty close, let's talk about that. We just looked at two examples. Relative short. In a relative short jump, I'm going to have an 8-bit displacement. So I can handle jumps that range from negative 128 to positive 127 bytes away. Relative near. If it doesn't fit in relative short, then it will automatically store the offset as a 32-bit value. Okay? So, the assembler is going to use a short jump when it can, but if there's no difference in how the instructions are encoded except for how many bytes are needed. Okay, before we get to conditional jumps, let me go back. So we had an unconditional jump that is a relative short. So relative short is, opcode is EB. So the previous instruction would be EB, FB. Okay, where that's the opcode and that's the offset. How far away or what value should be added to the instruction pointer to get me to the location that I need to execute next. Alright, let's do a little bit more conditional jumps. So, unconditional jump is helpful, but what if I need to say, I want to jump only if something has happened? Well, the x86 instruction set has a set of has actually several series of jump instructions that allows us to implement selection and loop structures in a low-level language. Each one of them has a format that looks like this. Jump on some condition code to some label. Okay, and I'll show you some examples so you'll see what those are. Okay, but these identify the condition under which the jump is to be executed. So if the condition holds, then the jump takes place. Otherwise, the next statement after the jump would be executed. So if the condition holds, we jump. Otherwise, we execute whatever comes after it. All right, so nearly all of the conditions considered are settings of the status bits and E flags. And here's something important to realize: the conditional jumps do not themselves alter the flags, they only react to the previous settings of the flag. So, simple conditional jumps. These jumps will jump based on one of the status bits and E flags. Okay? Now, you'll notice that some of them have multiple mnemonics. For example, jump if equal, jump if 0. They have the same opcode. They jump based on the same flag settings. This just helps with readability. Okay, same thing here. Jump if not equal, jump if 0. Same here. Jump if parity or parity even, no parity or parity odd. So anytime you see these, they're the same. It's just multiple mnemonics for the same opcode, just to make code a little bit easier to read, make the flow of execution a little bit easier to follow. Okay. All right, let's look at an example. We've got a checking account where when a transaction occurs, we'll follow a different course of action depending on what the resulting balance is. So here's the algorithm. I'm going to add some value to the balance. If the balance is less than 0, negative balance, we'll implement the design for a negative balance. Else, if it's 0, we'll implement the design for a 0 balance. Otherwise, if both of these two fail, then we will implement the design for a positive balance. So, if I have a negative balance, well, I'm going to have an insufficient check fee. I could get some other things happening. 0 balance, maybe I get a notice. Positive balance, probably nothing. It's going to be just fine. Happy for me. Now, I went forward, but I really didn't want to yet. Here's what I want you to notice when you, whoops, went too far back. When you're executing a design in a high-level language, if you'll notice here, I say if the balance is less than 0, then do this. So I am checking for a situation that's going to get me into this piece of code, okay? And in assembly language, we actually want to look for what is the condition under which I will not execute the following. So let me show you this, and then let's play with it a little bit. So here it is in some assembler where I've left out the details of what we do for negative balance, 0 balance, or positive balance, because I really want you to look at under what condition we're jumping. So I'm going to add value to balance, and here I've got the design for negative balance. So my question is, under what condition do I not want to execute that? Okay, well, and I'm not actually going to go there. I'm going to go here. So if no sign, jump if no sign, well, I've just added a value to balance if no sign. So my answer is greater than or equal 0. So my result was a positive value. If that's the case, then I want to jump to this label. Okay? So if my result was greater than or equal 0, go here. Otherwise, fall into the negative balance, then jump around everything else. Okay? So if I get here, again, I'm going to check. And notice, this is the only instruction that sets any of the flags in E, or status bits in E flags. So if I get here, then I'm going to say, okay, I got here because the balance was greater than or equal to 0. Now let's check if it's 0. If it's not 0, I want to go execute the positive. Otherwise, I'm going to execute the design for a 0 balance and then jump around everything else. So in both of these cases, I'm jumping around everything else. Okay? And it's only if I fail that check and that check that I would execute one of these designs. Okay? Alright, so let's call it a video on that one, and we'll continue with these next time.